Hey class, today I will be teaching you about binary search trees and why you should care about them. This video assumes you are already familiar with basic tree terminology. If you need a refresher, feel free to check out my video on trees, which I will link in the description. Here is an overview of what we will learn today. First, we will learn what a binary search tree is. Then we will look at some operations and do runtime analysis. Lastly, we will learn about why we should care about binary search trees. Recall that a binary tree is a tree where each node has at most 2 children, and a binary search tree, or BST for short, is a binary tree where every node is greater than all the nodes in its left subtree and less than all the nodes in its right subtree. Due to this structure, it is easy for a binary search tree to maintain order. Now, let's go over some operations, starting with insertion. Let's say we want to insert the number 20 into the binary search tree. To do this, we look at the root, which is 42, and ask ourselves, is 20 less than 42? The answer is yes, so then we insert 20 into the left subtree. Looking at the root of that subtree, we ask ourselves, is 20 less than 19? The answer is no, so we insert 20 in the right subtree. Looking at the root of that subtree, we ask ourselves, is 20 less than 25? The answer is yes, so we insert in the left subtree. There's no tree here, so we create a new node with the value 20. Something I want to point out is that these questions were all binary questions with binary answers, which might clue you into why this data structure is called a binary search tree. Now let's look at some pseudocode. Let's define a node as containing a left node, a right node, and a value, and we want to define an insert function. As we just saw, we can do this recursively. In the base case where there's no tree, we can just create a new node. Otherwise, if the value is less than the value of the root, we insert in the left subtree. Else, we insert in the right subtree. And then lastly, we return the tree. Now I'll play an animation demonstrating how this works for the example we just showed. Something that is important to point out is that insertion order matters. For example, if this is my insertion order, then I get out this tree. If I have the same elements and then insert them in a different order, then I get this tree, which is completely different. So for our runtime analysis, the insertion runtime is O of n because we could get a stick, but for a balanced tree, it's O of log n. Now let's go over lookup, which is very similar to insertion, and again, we are going to do this with an example. We are going to check if 74 is in the tree. First, we check the root to see if 74 is equal to the root. It's not, so then we check if 74 is less than 42. 74 is not less than 42, which means we should look it up in the right subtree. Then we check the root of the subtree once again. Is 74 equal to 80? It isn't, so then we ask, is 74 less than 80? It is, so we check the left subtree of 80. There is no left subtree of 80, which means 74 is not in the tree. Let's look at some pseudocode. For the base case, if there's no tree, then the value cannot be in the tree. If the value is equal to the value of the tree's root, then it is in the tree. Otherwise, if the value is less than the tree's root, then we should look in the left subtree. Else, look in the right subtree. I'll play the animation demonstrating how this works for the example we just showed. Again, the lookup runtime is O of n in general and O of log n for a balanced tree. With deletion, first we find the node we want to delete. Then there are 3 cases. Either the node has no children, has 1 child, or has 2 children. Let's go over each of these cases one by one. If the node has no children, then after you find it, you just delete it. Pretty simple. If the node has 1 child, then when you find it and remove it, you replace it with its child subtree. Lastly, if a node has 2 children, after you find the node, look for its in-order predecessor. That would be the largest node in the left subtree. Then, replace it with its in-order predecessor, and then reattach the subtree if there is one. You can also do the same thing with the in-order successor instead of the predecessor. That would be the smallest node in the right subtree, like so. You know the drill. The runtime is O of n in general and O of log n for a balanced tree. So why care about binary search trees? The structure of binary search trees make them great for storing ordered data, for example, a library catalog or an appointment schedule, and they are also frequently used in file systems and databases. There's just one problem. As we mentioned earlier, insertion order affects the shape of the binary search tree, so if we're not careful, we can get a stick which is less efficient than a balanced binary search tree. This raises the question, is there a way to guarantee balance? I'll leave that as some food for thought for next time. For now, let's summarize what we've learned today. We learned that a binary search tree, or BST for short, is a binary tree where every node is greater than all the nodes in its left subtree and less than all the nodes in its right subtree. We learned that binary search trees are good for maintaining order. For lookups and insertions, we recurse on the left or right subtree depending on the value relative to the current node. For deletion, we looked at 3 cases. If the node has no children, then we just delete it. If the node has 1 child, we replace it with the child subtree. If the node has 2 children, we replace it either with its in-order predecessor or its in-order successor and reattach the child subtree. The runtime of all these operations is O of n because we could get a stick, but it is O of log n if the tree is balanced. Lastly, we care about binary search trees because they are great for storing ordered data such as a library catalog or an appointment schedule, and they are applied frequently in file systems and databases. Thank you so much for watching, and please, feel free to comment any topics you would like me to cover next, or any feedback on how I can improve my videos. As always, this is your CS Professor of Fun.